All right, we're ready to get back. Uh, okay, a quick side note. You got the stuff I sent? You got the test thing? Scantrons up front. Take them on the way out. Okay. Let's see if we can get them back in by Thursday in lab at the end, please. If we can. At least you don't have to memorize the half-life of whatever. Okay? Just saying. With any good luck, my son won't call me for a while. It's okay. All right. So we will begin. We're going to pick up where we left off with digestive and try to get through a good deal of it today, and certainly by Thursday we should be able to progress on to the urinary tract. So for your not late but later arrivals, scantrons are up front, so you get this to me. Be much easier. I don't anticipate I will be here on Friday, so the last folks that I will see prior to our break are you folks, and that's all the news that's fit. I still don't have my computer back. They're telling me Wednesday, so if there's stuff that I need there, hopefully we'll have it on Thursday. So if I have any other information to share with you, that's located on that. And that's the introductory notes for this morning. Let us begin. We're all set. Glad to see you. Having an R&R day. The dog is at Camp Biol. He's running with the gang, which is good because my wife's at her mom's and too much running around today. All right, off we go. So there we are. We left off here. As you might recall, and yeah, I did pop that up. There is an outline at the bottom of week 4 where all the PowerPoints are. Again, I outlined this. This was the old number when I was teaching this course at CCAC. 2 locations. And it's got all the same stuff. It hasn't changed. Maybe there, so most of the information here is certainly relevant. So I would suggest that you take a good look at it and go run through it. I generally pull a lot of test questions out of this stuff. So be wary of it. Okay. So that's why they're there to help you. And there's no extra charge. Right? There's no charge for this. Again, you could be like, I used to ask my classes for Christmas presents. That's terrible to start with. And I said, I wanted those, I wanted to get a set of those Beats headphones. There's a class like, so somebody, they all of a sudden they come with a big box. In there were some Five Below headphones. That's the kind of people I've had to deal with. And I don't think you're any different than that. Possibly worse. That's the kind of, I don't get any respect. There's an old comedian now deceased. That was his tagline. Moving on. So we're dealing here with, and again, you're going to hear, many of you in micro are going to hear these same jokes again, even though you know you're coming. For the ones that I haven't had yet, make it look good. Oh, that was so funny. Grace is already troubled.
What do you mean?
We just know. Okay, it's all right. Moving on. So these are before we get to the small intestine, which probably has as much anatomy as any area. We have the liver, gallbladder, and pancreas. And again, we dealt with the pancreas a little bit in endocrine with insulin and glucagon and diabetes and all that stuff. This is the exocrine portion of the pancreas. It has more to do with the pancreatic, what they call juices, the liquids and materials that it secretes and enters the small intestine. So we'll get to that last. The gallbladder is relatively unimportant. It's more about what goes wrong than goes right, and the liver is extraordinary. Okay. The liver does so much for you. When it's damaged, you're always in enormous trouble. So these are all part of it. So livers, from a digestive standpoint, this is really where fats finally get broken down. Again, fats, it's not about breaking bonds, it's about separating the molecules. So bile is something that effectively, for lack of a better term, we call an emulsifying agent, which means it's bipolar. And so it can get in between molecules and separate the components that are there. We use them all the time in a variety of things, and certainly in our bodies, but also in everyday life. So emulsifiers are pretty interesting in and of themselves. So bile, and it's actually made from cholesterol, as you will see. The gallbladder basically stores it. It's non-essential tissue. It's more about what goes wrong. Are you better off with one than without one? Sure, but you can still be without one. And the pancreas is all about all the other enzymes effectively that are going to break something down, as well as, remember, it's all about pH control physiologically. The small intestine, where all these juices, as it were, flow in, is designed to be at an alkaline pH, a pH, let's say 8 or above, whereas the stomach is very, very low comparatively. I mean, the hydrochloric acid is pH 1 or 2. It's really strong. So you've got to neutralize all that stuff that's spitting out of the stomach, okay? And that's where that bicarbonate comes in. So that's part of it. So first you look at the liver. Liver is giant compared to everything else there. It predominates. You're talking about an average person, 3 pounds. I mean, it's not even close, anything that is that large. Anatomically, they divide it into quadrants. It's not important. Any part of the liver is identical to any other part of the liver. That's the interesting thing about liver. That's an anatomical thing in classic anatomy. Little pieces of peritoneum over time were called ligaments. One of them is called the false ligament or falciform ligament. It's really not a ligament as much as it's some connective tissue that they gave the name ligament to. So I don't really care about any of the lobes that are there. Okay, remnants of the fetal umbilical vein, doesn't make a big deal. So all of these things, just dividing it into different portions. But if you take a sample of the liver, anywhere in the liver, you take it here, you take it here, you take it here, it's all the same. And that's what we do. Medically, they do, and it with some degree of frequency, it's called a liver biopsy. It's a relatively easy, it's a bedside test under local anesthesia that you typically you'll see. I used to see them done over at St. Margaret's in Aspinwall in what they call the medical unit, which is really where they administer cancer chemotherapy and transfusions. And they'd have an area that was closed, and so we come in and they just basically poke a hole and take a little piece of liver out. The idea was it didn't, as long as you could access it, it all looks the same. So any piece, if it's showing damage, hepatitis, cirrhosis, would all look that way. You can see the gallbladder hanging down and sort of the undersurface or interior surface. And those ligaments don't really mean a whole lot. This area is really the indentations from pressure on it. It's mostly the inferior vena cava. I'm sure the aorta plays a certain, it probably doesn't play quite as much of a role as the vena cava, I would say. And you're going to see this is the important area here adjacent to it. That's called the porta hepatis. And so it's a port or a passageway in. There are two things coming in. The hepatic artery, which gives it all its arterial blood for energy to do well, it's very busy. And the hepatic portal vein, you might remember that when we did the blood vessels, all the blood that comes from the stomach, small and large intestine has to be sort of purified by the liver because it's anything but ready to go. There's just the potential for too many impurities, whether it's bacteria, whether it's toxins, and that's really an extraordinarily important job of the liver. And that's two ingoing ports. It's got an outgoing port, that's for the bile. So it comes out of the liver, and you're going to see when I show you the interior of the liver lobes, and again, one looks very much like the other. Okay, so it's held, all right, anchors to the stomach by the lesser omentum. There's the porta hepatis. And so this hepatic duct, the bile comes out. It connects, there's a little offshoot called the cystic duct that goes to the gallbladder. And then basically when the gallbladder rather releases it, it flows back into something called the bile duct where those two unite. You'll see the diagram. And I don't really get too involved with naming them, to be honest with you, because to me it's really not that terribly important. We'll get to where it's going when we start talking about something called the common bile duct. That's critical. And that's what we start to get. We'll get that down the road. And so maybe the best analogy I can give you, and I always use it, for what the gallbladder is for the bile is kind of like the like that overflow tank for antifreeze coolant in your car. You know how you pop the hood and you check it, and you should periodically to see if it's too high or too low or whatever. But basically, a fluid coming out, it basically has a, you load it and there's a passageway for fluid to come out, but there's also a passageway for fluid to come in. That's kind of what it does. I mean, we, when I say you like the gallbladder, you could do without. Years ago, when we first had, they didn't have that. That's relatively new. In the first vehicles that I drove, I know, a long time ago in a galaxy far, far away, I got my driver's license in 1968. I'm guessing none of you were born. Okay. She didn't hear. But we didn't have that. And so the car would overheat and you'd sit there on the side of the road with the hood up, waiting to pop the radiator so you could pour water into it and cool it down. It's a long time ago. It didn't matter. Gas was like 30 cents. Just saying. So you should be interested in that. I know. So here's that porta hepatis. In this case, the vein is going in, not going out. That hepatic portal vein goes all the way through all the areas of the liver, and when everything is processed, that blood comes out, let's say cleansed, if you want to think of it that way, by two things called the hepatic veins, one on either side, and join the inferior vena cava. So this is blood that needs to be attended to, and this is the blood after it has been attended to. And here you can see the outpouring here, what they describe with the hepatic duct and now the cystic duct that's over here. And when they finally all go out, okay, we finally get down to this way, now we have a bile duct. The liver is completely, if I could draw it here, and I won't because I'm not any good at it, and the illustrations are better, it looks like a hexagon, a six-sided figure. And you have a tiny unit of each of those vessels at the six corners of that. They call it the portal triad. So each corner of them, they call them lobules, and you'll see it first microscopically and then schematically, okay? And effectively, the arterial blood and the portal vein blood are flowing in and passing over all of these cells that address it. And basically, you want to say purify it, modify it, process amino acids into proteins, detoxify, all of those things, basically recreate structures and chemical structures that we're going to need either for breakdown or for other purposes in our body, clotting factors, all of that stuff. Everything they're making inside that liver. And then it all kind of flows from each of those corners to something called a central vein. Now the blood has been addressed, all the particles in it, and that's the final blood that's going to eventually make its way out into the general circulation by way of the hepatic vein. So again, the hepatic portal vein brings the nutrient-rich, not all good stuff necessarily, into it. This is what you look like, microscopic. That's an actual micrograph of a healthy liver. So they all look like that. And so when we see distortion, when these are irregularly shaped and there's bunches of them, it suggests that this is a process of inflammation or toxicity or damage in some way, shape, or form. Surely the liver is damaged by alcohol more than anything else, commonly. But when you hear about hepatitis A or hepatitis B or hepatitis C, those are all viruses that potentially can do damage. And that's just the ones we're most familiar with. There's D, E, and F. They're just not as common. For whatever reason, in viruses for the liver, we use letters, and typically for viruses, otherwise we use number, COVID-19. So typically viruses are tagged by numbers for whatever reason, hepatitis, and they're not all the same, as you'll learn about in micro. So here's a close-up. So at the edges, even though you can't see them, but everything goes to a series of tiny little, for lack of a better term, nooks and crannies. And the term I always use is percolates. It sort of drizzles through. Coffee percolator, is that ringing a bell? You know drip coffee, right? We all have the Mr. Coffees and the like. Basically, you're pouring water through it, it's dripping through. In the old days, percolating was the way we made coffee. You heated the water to boiling, and there was like a central tube. The boiled water would squirt up and come back down, and squirt up and come back down. That was percolating. So if you go to a function and they have one of those big coffee makers, okay, that's a percolator. Well, purists somewhat like perked coffee. We run on Dunkin' in my house. So those are called the liver sinusoids, the blood vessels. Remember we talked about shapes of capillaries. These are the ones with the wide openings, very, very leaky. Okay, lots of macrophages, lots of, these are basically taking out debris, taking out old red blood cells because the liver can do the job of the spleen, which also takes out old red blood cells. This is a really good image or illustration of it. Here you have a triad, etc., at this sort of hexagonal structure. So again, the two inflows are the portal vein and the hepatic arteriole and the portal venial, because it's so small. And then you have all these little channels formed to these tiny bile ductules because they're small. And basically the bile is being produced by the cells as it's processing. Bile is going out this way from the center out to the edge, and the blood going this way toward that central vein. So they have a lot of endoplasmic reticulum, actually a little more smooth than rough. Okay, a lot of that. They're very busy cells, a lot of mitochondria. We produce about, that's the better part, around a quart of bile a day, and it does other stuff. We can store sugars there. We can store fat-soluble vitamins. The liver's mostly fatty more than anything else, and the detoxification is really important. So the bile is made of a couple of things. Bile salts, which are derived, which is one of the ways we use cholesterol, and interestingly, we recycle it. Cholesterol gets a bad rap nutritionally. Okay, we went crazy years ago when they started to do cholesterol-free and cookies and stuff like that. That they were staying away from things that quote unquote had cholesterol. They supplemented it with high amounts of sugar. Go figure. They had cookies called Snackwells. And everybody was saying, "Oh, it's fat-free, cholesterol-free, filled with sugar, worse-free." We take the cholesterol we get naturally and we make the bile salts from it because you need a fat to separate a fat. And we recycle about 95% of it, as you're going to see, in something called the enterohepatic circulation. Just have to know basically what it does. And the bilirubin is from the heme. We can recycle red blood cells. We can recycle the globin. We can recycle a great deal of the iron. We can recycle all the other stuff in the plasma, but we can't recycle that heme that the oxygen sits on. So that heme is broken down in the liver and eventually forms something called bilirubin. That has an interesting color, just the way when you see a bruise breaking down. You know how it discolors, you get a black and blue mark, and it changes colors. This does also, and it gives the color to urine and feces. So we excrete it in the urine and the feces. Voila. Here's the enterohepatic circulation. So again, we reclaim about 95% of the bile salts. Years ago, they thought it was a good idea for people with high cholesterol to target this pathway. Oh, we're going to stop this enterohepatic pathway and make sure that way we'll get rid of more cholesterol for people with quote unquote high cholesterol. Good idea, bad result, because it made the liver work extra hard. And they actually were, so the cholesterol medicines today work a little bit differently. I would wager that any of your older relatives are on atorvastatin, which is known as Lipitor. Okay. So if you ask them, are you on any cholesterol medicine? Most of them are going to be on something that says atorvastatin. That's the generic name. And it works differently. I don't think it's necessarily that great. That's me. It gave me a bunch of headaches. I said, my family doc, who retired, thankfully, because he kept yelling at me. I went there. He goes, well, let me see. You're 70 years old. He goes, and he starts punching things on a program on his phone. And he goes, if you take this medicine, you'll have a 25% less risk of having a heart attack or a stroke. It's like a sales pitch. You buy this, you're going to have a healthier life. So I started taking it. Sorry, didn't buy it. So here's the circulation. So the bile comes from the liver, collects in the gallbladder, released into the small intestine. This neat structure is called the common bile duct. Talk about that in a second. It's got a different name now. Travels all the way through, does its work, and when it finally gets back down about here near the end of the small intestine, it gets sucked back up to be recycled. That's what's meant by it. And so here are the bad things that happen to your liver. Typically viral, drug toxicities, poisoning. One of the things that poison mushrooms are known for, create problems. If you're into mushrooms and you're into foraging, know what you're doing. Okay. If you don't know what you're doing, don't be picking mushrooms and bringing them home. Okay. Around here, there's a lot. This would surprise you that my wife and I joined the Western Pennsylvania Mushroom Society for a couple of years and went on these foraging episodes. It's not that funny. Have you ever had morels? They cost like $25 a pound. A little butter, a little garlic, pinch of thyme. Mushrooms love thyme. Mushrooms love thyme. Squash loves sage.
What?
Terrible. What? So you see these things, whenever we went out, they always had someone from the club, and they told us the same thing. They said, "Look, if we're not sure, we'll take a picture of it. We'll send it to somebody. Hold on to it." They say, "Don't eat it. Don't eat it." I mean, it's the way it works. You gotta know what you're doing. Okay. I give up. Next thing I ask about truffles, and you'll not ruffles have ridges, but truffles. All right, moving on. So typically, if it's chronic and even if it was hepatitis, the end point is the same: destruction of the liver. It becomes chronically inflamed, and it can be from viral infection, but again, more commonly alcohol. Over time, the liver goes from fibrous to fatty in nature, and then it begins to deteriorate, and that's when it becomes what we call cirrhotic. So cirrhosis of the liver it takes a long time for that to occur. That's serious drinking. On average, that would be somebody having a bottle of whiskey a day for 10 years, a bottle of wine a day for 10 years, 6-pack a day for 10 years, every day. I mean, when I say serious is serious, and there's plenty of people who do that, unfortunately. Okay. One of the more difficult addictions to deal with is alcoholism. That are there, and the trouble with hepatitis is it stays with you. If you're exposed to it, again, when you see someone who tests positive for hepatitis B or hepatitis C, all it means is that you've been exposed to it. Most of us have been exposed to hepatitis B because of an immunization. Okay, and you'll have a titer, which means a level of antibodies. That basically tells you you're protected. Okay, it also means you have the virus inside of you potentially. When you see if someone has active disease, you look in the bloodstream to see if there are viral particles. That's the way they look for active disease. And there's a big distinction between them because it can be harbored there and become active at any time. So be wary of that, particularly if you're working in a healthcare field. That's why they give you a chart to read about a patient. To understand if they've got something that you have to be extra special careful, do so. The fact that they're HIV positive just means to make precautions. It's very unlikely from a random needle stick in someone who's HIV positive, like 1 out of 500, that you could get HIV. If someone has what's called chronic and persistent hepatitis C, or for that matter, AIDS, different diagnosis, it is likely from a blood splatter or a needle stick that you would get that virus. Be aware of that. I mean, that's part of what I try to do here is to give you an idea of how it's all about exercising a certain amount of due care. So we'd have folks like that back in the old days before we even heard the words HIV. Okay, if it was mostly syphilis and gonorrhea and those are the things that are in the bloodstream, sexually transmitted diseases, we'd be double gloving for surgery. So moving on. So, and what happens is now what they call portal hypertension, pressure builds up in the liver because the blood effectively can't get through there and it backs up and it creates a lot of problems. And what happens when any of this happens, that bilirubin, the breakdown product from the heme, gets into the bloodstream. It's got nowhere else to be disposed of. It can't be excreted. And so and that's what jaundice comes from. So we see jaundice relatively normally with something called ABO incompatibility. We talked a little bit about that with blood types. Sometimes the mom and the baby have a slight incompatibility. It has nothing to do with that erythroblastosis vitalis, the positive and the negative incompatibility. This is just a subtle antibody-based incompatibility. So they'll develop, babies will be born somewhat jaundiced. They generally can get rid of that with ultraviolet light. That happened to the son who just called when he was born, these many years ago. We adopted him. So he's in ICU for the first couple of years because he was very much of a preemie. Okay. And on the other side, when we see that in an adult, then you start worrying about liver disease, gallbladder disease, pancreatic disease, chronic alcoholism, etc. So nowadays, we used to have donated livers. Now livers, we can do live liver transplants because the liver is highly regenerative. It's the cells are nearly identical, but we call them relatively undifferentiated. They just have a general job that they do very well, but there's not a lot of, it's not like a muscle or a nerve cell, which is very much highly evolved, if you want to think of it that way. The gallbladder itself is a sac, and again, when it's empty, it's got a lot of folds, and there's a lot of little nooks and crannies, again, and when crystals form in certain individuals, gallbladder bile will crystallize and form something that you've all heard of called a gallstone. And remember, it's a sac that's powered by smooth muscle contractions. When food enters your small intestine, you generate a hormone called cholecystokinin. Kinin means make it move or make it active. Cholecysto means the gallbladder. It's not the only thing it works on. But what it does is it causes the gallbladder to squeeze and eject bile. It's like, hey, we just had lunch. Stuff's coming into the small intestine. Send us some bile because they probably had, a cheeseburger. So the cheese being fatty would have to have some of that agent. Okay? That's really kind of the way it works. Because of the honeycomb nature of it, they can get trapped in there. And then whenever you have smooth muscle that can't contract or is impeded because something is obstructing it, it causes the muscle to go into spasm. We have a great word for spasm. Any of you who have babysat probably heard it. It's called colic. So if you babysat, okay, you had a colicky baby. That meant that their digestive system would periodically go into spasm. I had 2 of them. Thankfully, my daughter was not. So the idea, you get that those spasms are very, very painful. So they're called calculi. That's the name for a stone. Cholesterol, bile salts, anything that does fatty things. With the exception of one gentleman in the room, it is much more, not that it doesn't occur in men, it is much, much, much more common in women. Like 80-20. And there's a lot of difference, so we see it in a lot of women, and there's a certain degree of risk factors. We used to think that it was older, can happen in younger too. My daughter-in-law had to have her gallbladder removed laparoscopically, fortunately, almost immediately after she gave birth to my younger granddaughter, the one who's 6, because she was conceived by IVF, and they have to give you a lot of significant cholesterol based, like estrogen, progesterone type lookalike stuff. And that just causes havoc with your gallbladder. When they did it, fortunately for the next child, it was not nearly as big of a problem, but she was in trouble. So, I mean, she didn't get out of the hospital for quite a while. So here's the obstruction. It can be anywhere where those stones, anywhere along the duct. They can clog the pancreas, etc. And just like you see when we talk about urinary stones, bladder stones, and particularly ureter stones, there are agents that can dissolve. What they use a lot of today, because it's non-invasive, is lithotripsy. They use ultrasound, high-frequency sound waves, the same ultrasound that many of you will be familiar with from a standpoint of what you're doing professionally. And those high-frequency sound waves, and you have somebody basically in a large kind of special tank of water, because obviously the sound waves travel better, will target those areas and try to basically crush those crystals, pulverize them with the sound. Okay, and people are somewhat sedated but awake. That's saga for the gallbladder. Pancreas. Okay. We've already done the endocrine function. This is the exocrine function. It's kind of under and underneath the stomach. It's the head of it. It's got a tail that's more underneath the stomach. The head of it is really encircled by the first loop of the small intestine called the duodenum or duodenum. And our concern here is this: pancreatic juice. They produce tons of bicarbonate, water, other electrolytes, and particularly enzymes. Enzymes, just like we learned about in the blood clotting thing, are produced in their precursor state. We call it the ogen state. So the nickname for enzymes that are inactive is zymogens. And they are activated principally once they get into the small intestine by a variety of factors. If they're activated where they shouldn't be, they're protein digesters. It doesn't matter where they are. A protein digester is indiscriminate. It'll digest muscle, it'll digest bone, it'll digest anything that's got protein in it. Okay. And so that's one of the things we see in alcoholics particularly, and sometimes post-operatively, this happened to my first wife. Okay, when she had a tumor removed, she got pancreatitis. And that was mechanical because they had to remove it from the back of the pancreas and start to leak these enzymes. She was doubled over in pain. We had to carry her back to the hospital post-op. Ouch. Okay. And so there's just a whole bunch of channels like that. They're very busy. Lots of endoplasmic reticulum, mostly rough here. The liver is mostly smooth. And all those granules are secreted in there. Okay, and you see the composition. We make a fair amount. It's like 1.5 quarts, pH 8, neutralizing stomach acid, electrolytes, bicarb, and the enzymes. And so this is where the small intestine gets all of those enzymes, not all, but nearly all the enzymes, to digest proteins, starches, which in starches we just started in the mouth. Other than that, we haven't touched them. Chemically, lipases, we had a little bit in the mouth and a little bit in the stomach, and nucleases, we haven't touched at all for nucleic acids like the A's, the T's, the G's, and the C's. So they're inactive and then they're activated. So once it gets into the duodenum, you're going to see this is a special enzyme. Entero generally implies small intestine. Peptidase, generically, these enzymes that break apart polypeptide or peptide bonds, and it activates them. And so the big one is called trypsinogen to trypsin. And then once that's activated, the other ones, procarboxypeptidase and chymotrypsinogen to chymotrypsin. There's a variety of it. Anytime you see any of those names, trypsinogen, procarboxypeptidase or enteropeptidase, pepsinogens like that. All of them, the implication is protein digesting enzymes from a test perspective. You don't have to remember all they are. Well, the names, if you feel like it, go ahead. And this is the magic, is right here. The single most important part of your entire digestive tract is right there. The common bile duct. That accepts not just from the pancreas as pictured here, but coming down from the liver and the gallbladder, they join together. In the old days, we called it the common bile duct. Now we have a new name for it. It's called the hepato for liver, pancreatic ampulla. So here you can see it. They fuse together at the wall of the duodenum, and this is the name of the structure. It opens into the duodenum. It kind of looks like the top of a volcano is the way they describe it. I've never seen it. And there's a little sphincter behind it that controls the flow of the bile and the pancreatic juices. And what triggers it, pardon me, again, anything that goes into your gut, there's the major factors that triggers it. So food's leaving your stomach, it starts to stretch the small intestine. That triggers it to allow the common bile duct to pour stuff in. The stuff that comes out of your stomach is highly acidic. That triggers it in little spurts. The stuff is highly concentrated, so we call it hyperosmotic. So the amount of particles per unit are very, very high. There's sensors for that. So you have chemical sensors, osmolar sensors or osmotic sensors, and pH sensors and stretch receptors, all of which are basically saying, hey, got stuff coming in. And this, you'll see this diagram at the final. Here you can see the gallbladder, the hepatic duct, the cystic duct. Now it's formed the bile duct, coming all the way down, joining the pancreatic duct. Here's the sphincter that controls it. It's just coming together, a smooth muscle. And here's that, quote, volcano-shaped structure. And there's the opening. There's even a lesser opening farther down. But the duodenum or duodenum is relatively short. It's only about 10, 12 inches. Subway, foot long. Context. Unless I miss my guess, everybody eats, right? For the longest time, I didn't think my daughter did, but now it's different. And I was convinced my sister didn't. She still weighs 97 pounds. She weighed that in college. It's not right. I have a leg that weighs more than that. Oh, I can't fit into a size 2. We'd see she eat like an open-faced sandwich. Oh, I can only eat half of it. I'm full. Really? That's one bite to me. It's pizza. Again, I always cut pizza into 6 pieces because I can't eat 8. Makes sense, doesn't it? Oh, 8's too many. I'll make it 6. The chemicals, just like gastrin, if you remember, and histamine, if you remember, and acetylcholine, if you remember, for the stomach, the 2 chemicals that regulate all of this are, again, cholecystokinin, which does more than just trigger the gallbladder, though that's its name, and secretin. Secretin is this sort of magical hormone that when the small intestine is stretched, triggers a variety of structures, not the least of which is the pancreas, to get busy. So what makes it happen, okay, if there's a lot of enterohepatic circulation going back, recirculating the bile salts, that means things are busy inside. Secretin from cells in the intestine, when they're exposed to the hydrochloric acid and the fatty chyme that comes out of the stomach, they trigger it. So once digestion is active, that sphincter opens and then it is released into the small intestine. And they give you the whole pattern of this. And if you want to read through it, go ahead. And then voila, that's done. And so the last part of this digestive presentation. And so, and again, for our purposes over the next, so I will finish this and we'll probably get well into urinary, at least the start of it. Not so much the function, probably till we come back from break. And then we have male and female reproductive. We're done. All the stuff we're doing. And that'll be in the 2 weeks. And unfortunately, I think our final is early. I think we got the Monday. So you'll be busy the weekend before. Let's see. The most important area, as well as the common bile duct, this is where the vast majority of chemical digestion and absorption occur. Nearly everything that we absorb that's useful, whether it's amino acids, whether it's simple carbohydrates, whether it's nucleotide making materials, all of that comes from the small intestine. This is where most of the finalization of digestion, we started, but the vast majority of chemical digestion is also here. These numbers are incorrect. They're talking about a limited portion of this. It is longer than 7 to 13 feet. It's probably somewhere between 12 and 20 feet. So I'm not sure how they got those numbers. I think it's misprint. I always point that out. So from the end of the stomach to what's called the ileocecal valve is roughly 12 to 20 feet. And it's so much larger surface area. This is this remarkable area that's about the length of let's say a 20 or 25 foot garden hose, and about that dimensions, about an inch or so in diameter, that if you slit it and you slit a garden hose, you could lay it out. And it wouldn't look like there's a whole lot of space, but with all the structural adaptations for surface area, it has effectively the surface area of about the size of a tennis court. So it's immense. There's an immense amount of surface area and cells dedicated to chemical digestion and absorption. And so it's an extraordinarily important. We need it. I mean, if there's something wrong with it and you'd have to cut a piece out, you'd have to sew it back together. Okay? Because there's only certain things we can go through. When we get to the colon, that is non-essential tissue. You can live without your colon. The colon basically sort of finalizes what you're excreting, the feces, maybe a little bit of water, a little bit of electrolytes, a little bit of vitamin production, all of which you can supplement elsewhere. So I know people have had to have because they have a disease, terrible immune disease called ulcerative colitis. And this gal I know we used to go out back in high school, had to have her whole colon removed. It was so bad. Not a great way to live, but what are you going to do? So you can see it's maybe an inch or so, inch and a half in diameter. And so it has three portions. The duodenum, however you want, I pronounce it that way. Some people say duodenum. Mostly retroperitoneal. Again, the common bile duct is a stability point. It needs to have, when I think of important structures, I think they need to have stability points that are there. And then the next areas you can see, this is less than a foot, but 8 feet and 12 feet where I come from, that's 20. Okay. And obviously there's some variation. Then it has the jejunum and the ileum, and they all are pretty much identical. The only exception is because the bile duct is here. Everything else basically looks the same, and you're going to see the structural adaptations that permit this vast amount of surface area. So there's the duodenum, that sort of purplish color. In this one shade of blue is the jejunum, and then in this sort of reddish kind of a color is the ileum. And you can see it ends here at the start of the large intestine, which is about a couple of times wider and pretty distinct because of these little pouch-like structures. Right there where the appendix comes off, the first unit of the large intestine is called the cecum, C-E-C-U-M. So the name of that valve that allows flow out is called the ileocecal valve. So you go all the way from here, pyloric sphincter, to the ileocecal sphincter or valve. So there's a lot. Again, same illustration you saw before. And the first thing to note, this is not quite 100%. It's not like circular ridges. They sort of spiral. They've got a fancy name. They're called plica circularis. So they are circular, and plica, or application, is a fold. So when you plicate something in surgery, you're sort of shortening it and folding it. And I'll show you what it is. Now, we looked at the blood supply before, mostly superior mesenteric, maybe some inferior mesenteric. Nerve supplies, almost parasympathetic and sympathetic, not going there necessarily. This is the whole idea for this immense amount of surface area, and they've calculated out for the average intestine. So these circular folds, or plica circularis, don't just go like this, they kind of gradually spiral down. So that means the food that's squirting in, the chyme that's squirting in, is slowly contacting those areas. So it's not like a hose and you're shooting something through it, or a straw. It's going around. You used to have one of those things at the Science Center where you put a quarter in and watch it. We still have it. Do they?
I think so.
I mean, maybe. My first wife worked there back in like 98 to 2000. And she was like a party presenter, like for birthday parties, and those people who go to demonstrate that stuff. That's where my eldest first became acquainted, because she got him a job working on the submarine museum, and that sort of stimulated his interest in the Navy. And obviously, was fairly successful. So those folds, about a centimeter deep, not very deep, less than a half an inch, force the chyme slowly spiral, more time for absorption. It's being spun over little finger-like, 1 millimeter, little bumps that you could barely see all over. It's like you rubbed your hand on something and it will have all these tiny little bumps. They're called villi because they remind an anatomist of fingers. And on top, surrounding it, front to back, side to side, all over the entire surface area, are specialized simple columnar cells with microvilli, which are additional infolds that all increase surface area. And that's called, and it looks like a brush border because it's kind of fuzzy when you look at it microscopically, and they make enzymes. If you remember way back when you started A&P, when you looked at the different things that were on the cell membrane, they had enzymes, was one of them. And these brush border enzymes are classic because they're the final step. So if you have sucrose, okay, regular table sugar, and you put it on something, when it finally is digested, we can't digest the sucrose. It's a disaccharide. We have to break it down into its components, glucose and fructose. So those enzymes are there in that brush border. So they have sucrase and they have lactase. And when you hear about someone being lactose intolerant, because they don't have that enzyme, and then the lactose, the milk sugar, or the dairy sugar that's in all kinds of dairy products, creates a problem inside. And it irritates the lining, and everybody gets the things you see people who are lactose intolerant. This is kind of what it looks like. And you see a couple of examples. So you can see how it's circulating around, but spiraling down. Here are the muscular layers, circular and longitudinal. Blood vessels, sure. All those indentations, those little clefts that are in there. And then you can just start to make out those little nubs. This is what one of those nubs looks like. So it's a little finger where it gets its name, and surrounded all over the little blue are goblet cells, but these are simple columnar. Millions upon millions of cells. We probably slough billion or more cells every day of these lining from stomach, small and large intestine. Constantly transitioning. Every roughly 3 to 6 days, they're all replaced. It's an onslaught of chemicals and enzymes and acids and bases. Can you imagine having to put up with that for a couple of days? You go, oh, I'm done. I quit. Your cells do the same thing. Oh, I'll see. I'm leaving. The cell can't go to HR and complain. I'm being untreated unfairly. As far as I know, there's no union for simple columnar goblet cells. There may be. Not great. Not funny. No laughing there. You want me to go back to the Mushroom Society stuff? I'll try it. Look, I can't be scintillating every day. Just ask my wife. You already said that joke. Thanks a lot, dear. Love you too. And so inside, remember we talked about this a little bit in lymphatics. Inside each of those fingers is a lymph vessel called the lacteal surrounded by a capillary bed. So this can absorb the fats and specific things that don't fit in the blood vessels, and it has the blood vessels. That's what it looks like. There's the microvilli, all those granules of brush border. Okay. This is pertinent, particularly when we talk about radiation biology, or the problems when you're all those wonderful products you're learning about for people who have cancer or will be. Okay, in those areas, in that small intestine, there's little indentations that go farther down. They're called intestinal crypts. That's where all of these cells are produced. Extraordinarily busy reproductively. Probably other than pre-birth, this is the busiest area in any of us. That's why it is the most susceptible area to damage from radiation or chemotherapy, period. It's a lot. That's it. It's in our radiation biology course, which I am teaching also. So they are bound by tight junctions, just like the stomach, so those chemicals don't seep through. Absorbing nutrients and electrolytes, they produce additional intestinal juice, all the things that are there. Mucus from the goblet cells. Just like the stomach, they have enteroendocrine cells. That's where the cholecystokinin and secretin are produced. They're scattered in the villi, but there's also some in the crypts. Inside, they have these Paneth cells. They're special in the sense that they produce localized chemicals that are antimicrobial. So what you eat is not sterile. When you cook something, you didn't sterilize. So if for you carnivores, if you're having a burger tonight, okay, you typically heat it to an internal temperature of 160. Ground meat, chicken, same thing, about 160. Effectively, you're destroying all of the bacteria that could cause full-born illness. It's not 100% true. I mean, there's still stuff on there. And sometimes, if it's not cooked properly or prepared properly, or it's contaminated, it's trouble. Okay, the pan cells have additional reinforcements, and the stem cells, you can see epithelium every 2 to 4 days. So, additionally, Peyer's patches, lymphatic nodules, great numbers. The farther along you get, because bacteria increase. Okay, IgA is also there. That's that immunoglobulin we have in our secretions, saliva and mucus. We have it everywhere there's an opening. So in your mouth, in your nose, rectally, vaginally, urethral, all that. And then additional glandular structures, and this is the big nugget. Chemo and radiation therapy all target this. Okay, rapidly dividing. The more rapidly mitotic it is, the more susceptible it is. Because effectively, those cells are the busiest cells. They gobble up bad stuff. They gobble up good stuff. It's what I call the ravenous dog theory. So if you have a dog that's starved, it'll eat anything, right? A very well-trained dog will only take food from its handler or it's my dog, its person. Typically my food. Head, knee. Okay, what do we have for dinner? Okay. And so, and this accounts for all of those things. So that's one of the, to me, the pitfall of treating cancers, the traditional methods, although it's all we had, effectively we were playing a dangerous game. We were trying to kill the cancer cells before we killed the good cells. It didn't always work. First autopsy I saw was unfortunately a homeless individual who was being treated, okay, for liver cancer and ended up dying because it damaged his lungs to the point where he couldn't breathe. So moving on. So the liquids are intestinal juices, anything that stretches, irritates, respond. And basically it's the chyme coming in. Again, it's acidic, it's hypertonic, it's very concentrated. And so those juices are alkaline to neutralize it. Water, mucus, protective in nature. 3 to 6 hours for the small intestine to basically do what it has to do. So, I mean, when you're thinking it's 4 to maybe anywhere between as little as 2, as much as 8 hours in the stomach, and 3 to 6 hours, it gives you kind of idea of the processing time. And so these are all things that come from the liver and pancreas. Bile for fats, bicarbonate from the pancreas, all those digestive enzymes, not the brush border ones, they're in the border of the small intestine. And they're the final step. And again, there's tiny little squirts because you have to adjust the pH because it's so acidic coming in, it has to be neutralized. That is there. And there's a variety of reflexes. And that's where we see, in addition to the processing, peristalsis and segmentation. Why it's in there typically longer than your stomach is this is where you're maximally digesting and absorbing. So it's not just being pushed and pushed and pushed. It's a lot of that over and back. Remember the segmentation? Back and forth in these segments to really maximize processing. And so, again, you can see the different phases, and they talk about migrating motor complexes, and nobody cares. Nobody cares. And it finally gets to the end, the ileocecal valve, and once it's there, okay, basically it relaxes and emits it. And when that happens, it's almost like it's almost like when something enters your stomach, sometimes you feel the urge, you have to run to the bathroom. That's called the gastroileal reflex. It's almost like saying, hey, idiot's eating again. If you got to go, go now, because I'm sure he's going to have like 3 pizzas and a burger. Again. You guys do eat. I give up. Nobody likes you. Good. This is quick. End of the digestive. Not some of the physiology, not. Large intestine has basically is all about nearly everything's done absorbing water as necessary to basically finalize the consistency of what you're going to excrete. Some vitamin production, okay? Basically, some fat soluble vitamins are produced there. A certain amount of electrolytes are there. So it's not essential tissue. It's only got a couple of little points where it's retroperitoneal just to create the shape. What gives it its characteristic up, across, down shape, and then sort of coming to the inside are called the tinea coli. They're erroneously called the tendons of the colon. They're really 3 smooth muscle bands that help it hold its shape. The little segments, they're like pouches, are called haustra. The only one that has a name is the first one, the cecum. It has little fatty globules kind of hanging off. You'll see the illustration. We don't even know what they do. And so the cecum is the first part. How do you know the cecum? It's where it's being entered from the ileum, and it has this massive lymphoid tissue called the appendix or vermiform. It's kind of spiraled, so stuff can get trapped. We used to remove them all the time. We don't remove them nearly as fast now unless they're really bad. You kind of wait on it. because we think we sort of replenishes the gut with bacteria after somebody's had like about a colitis or diarrhea from something they ate that was really bad for them. It goes up, it's called ascending, it goes across, it's transverse, it goes up on the right, transverse, down on the left, and then sigmoid, because there's like an S curve coming in toward the middle. And where it turns, they're called flexures. So you have the hepatic one or right by the liver, the splenic one on the left. Okay? And then finally the sigmoid, because it's got an S shape, and it kind of takes it from the exterior kind of centrally into the abdominal cavity. And then it leads into a straight area called the rectum, and that's where the transition from sort of inside to outside kind of works, because you go from simple columnar now to stratified squamous, non-keratinizing. Okay, and you have sphincters there. So this is what you see here. You can see how the appendix points toward the umbilicus. So a lot of times one of the keys for appendicitis is you get pain toward the umbilicus. That's there. And when they're red and hot, oh boy, scary looking. Here's that Taenia coli, and there's 3 of them. Here's just showing you a color. Here's those epiploic appendage, and each of these is a haustrum or hausstruck. And then it just shows you the ridging, and those are what makes hemorrhoids in some people. A lot of things cause that. Okay? Not a whole lot to say after that. You can see how it's sort of all together, up, across, down, etc. And you can see when it kind of ends, it's the central idea of the ending comes in. Here you can see the sigmoid colon is sort of centralizes. And it's a pretty good illustration that shows you all those mesenteries, all that interesting visceral peritoneum sort of holding everything in place. So I think that's useful. And here's the appendicitis nugget. See it mostly in adolescence. Lots of things can happen, okay? Particularly if it ruptures. And let's stop it here. All right, we're good. I'll finish up digestive and start renal on lecture on Thursday, and we'll do a little bit more in lab. And don't forget to take a Scantron as on your exit.